So today we can start the oxygen family. So it is a 16th group, we know that. The elements which are present in the 16th group is oxygen, sulfur, selenium, then it is tellurium and it is polonium. Polonium is radioactive and it is a half-life of, very short half-life of 13.8 days. So it is radioactive. So generally we used to discuss the properties of sulfur, oxygen, selenium and tellurium. So these elements, they are present in the 16th group in the periodic table. So if we discuss that the properties of these, because I have told you that selenium, that is polonium, is radioactive, so we won't have to discuss much on that. Because polonium is formed as an intermediate in the decomposition of, that is radioactive decomposition of uranium and radium. That is what we used to say that. So that is in a radioactive series, we used to say that. Now we can say that the elements which are present in this group is, we used to say that the elements are, we discuss as the elements of this group. That is, we used to say that the oxygen, the sulfur, the selenium, that is the tellurium and the polonium. These are the right elements which are present. That is sulfur, we know that this is oxygen, sulfur, selenium, and this is tellurium, and this is selenium, tellurium, and we said that it is polonium. This is polonium. So these are the elements which are present in this group. The electronic configuration of these is, if we write the electronic configuration, we used to write that the electronic configuration of we used to write is, that is N is 2, we used to write that is P4. So there is 4 electron in the P subshell and the 2 electron in the S subshell. So the total valence electron are 6. Obviously, we'll say that they will show the 2 type of oxidation states. It will be the +4 as well as it should be the +6 oxidation states. So let us check that what is the electronic configuration is. So if we write their oxidation state on the basis of we'll write that on the basis of these, then we'll check that oxidation state. First we'll check that these two are non-metals. These two are metals, that is metallides. So this is metallides, we used to say that, and the polonium is a metal. We used to say that this is the metal what we have, the polonium. So what we write is, this is the metal what we have. Now we can say that if we talk about that, this group elements are also called chalcogens, and the elements are called collectively they are called chalcogens. They are called, right? That is chalcogens. So chalcogens, they are collectively called as chalcogens, as the nitrogen family are called pentacogens, because they are called, ores are called penicides. These the ore which is in which these are present are called chalcosides. So the oxide ore are generally called as the chalcosides. The sulfide ore are called sulfide or sulfate ores are called as chalcosides. So the ores in which these are present are called chalcosides. So we say that they are called chalcogens. So we can write that. Now their occurrence. If we talk about the occurrence of these elements, we can say that the occurrence is like this, we can say. So the occurrence of these elements, we used to say that is like this, that is, oxygen is most abundant on the earth crust. That is, we used to say that oxygen is most abundant on earth crust. So it is abundant on earth crust, we used to say that. Earth crust, that is around 46.6%, and it is also present in the atmosphere, that is, and also present in atmosphere, that is around, we used to say that 20% by volume. So we used to say that it is present in the atmosphere also, that is around 20% by volume. We can say that about that occurrence of oxygen. So, however, sulfur is present in the earth crust. We'll say that, however, the sulfur is present in earth crust. Earth crust, we can write that is around 0.03 to 0.1%. So that is how we can say that. That is in the form of minerals. That is, we can write that such that in form of minerals, like right, we can write that minerals. So the minerals, like we used to say that is galena, that is PBS. The galena, that is PBS. Then we can write that cuprites, and that is ZNS, that is, we'll say that galena. Then HGS, then it is, so these are pyrites, that is mercury pyrites, copper pyrites. We can write that CUS, that is called pyrites. So you just write that they are pyrites, HGS, pyrites, that is copper pyrites. Then we can write that mercury pyrites, these are pyrites, we used to say that. Then we can write that that is, we'll say that it is galena, that is, then we can write that zinc blend, that is ZNS, is called zinc blend. Zinc blend, we used to say that. Then we can write that even the sulfates, like we used to say that barium sulfate, PaSO4, that is also sulfur present in this. They are called barite. So that is barite, we can write like this, that is brighter water, we know that. That is called the brighter water, the barium hydroxide. So we can write that barium. Then gypsum, that is calcium sulfate. So we'll just write that that is calcium sulfate dot that is calcium sulfate dot 2H2O, that is called gypsum. Gypsum, and also we can write that it is magnesium sulfate MgSO4 dot 7H2O, that is called Ipsum. We know that. So that is called Ipsum, and also in the volcanic eruptions. In volcanic eruption as H2O. So in volcanic eruption, the H2S gas is liberated. Eruption, the H2S gas is liberated. So that is how we are able to write that what is the abundance. So sulfur is present in the earth crust, but its percentage is very less because it is present in form of minerals. These minerals are called chalcogens. So that is what we can say, that the copper, that is cuprous sulfide, we have written that, but the copper pyrites are different. The copper pyrites is like this. You write that mercury pyrites, and the copper pyrites is like this. The copper pyrite is CuFe, or you can write like this, that is FeCuS in this, that is the copper is in +1 state and Fe in +3 state. So it is copper pyrites. So I just want to write like this, that is there. So it is like this, the copper pyrites is, this is the copper pyrites. So that is how we can write the occurrence of sulfur and other elements which are the selenium and tellurium. We say that as selenites and tellurides and sulfide ores. So, and then we can say that the selenium and tellurium are present in, right now, present in the celerides. So there is celerides and tellurides. Tellurides sulfide ores. They are in form of sulfur, sulfide ores, whereas the polonium is, whereas we'll write that the polonium is formed as, whereas the polonium is formed as a decay product. As a decay product, we can write that a decay product in disintegration of that is thorium and uranium series. Decay product, that is decay product in disintegration of, so decay product in disintegration of series of, so in disintegration series of thorium and uranium. So that is thorium, you can write that, thorium and uranium, you can say that. So that is how we are able to write that the existence or the occurrence of these elements in the earth crust is. So polonium does not occurs in free state in the nature. It exists as like that. So we used to say that it is polonium is. So as I've told you that polonium has a half-life of that is 13.8 days. So it is having very less half-life. Half-life, you know that the initial amount of any substance will become half due to the disintegration is called its half-life. So if you take 5 gram, it will left 2.5 gram after 13.8 days. Then after next 13.8 days, it will become, that is 1.25 grams. So like that, that is what we call that half-life is. So that is a polonium. We used to say that it is having a very less half-life. So next we can write that is the occurrence what we have written. Now if we talk about their physical properties of these elements, so I'm going to write that the properties of elements. So if we talk about the properties of these elements, we can say that of elements, first we should discuss that what are their oxidation states, what are their melting point, boiling point, that is what we have to write. So if I write the properties of this element, that is oxygen, sulfur, selenium, tellurium and polonium. I'm going to write their oxidation states. What is the oxidation state they used to get is, in oxygen we used to write that it is -1 to -1, -2, -1, +1, +2. This is the oxidation state that is shown by the oxygen. Similarly, if I write for the sulfur, it will be -2, I'll write that. So it will be -2, then it is +2, +4 and +6. This is the oxidation state of sulfur. Similarly, I can write that for the selenides, that is +2, +4, +6. Tellurides, that is -2, +2, +4, +6. We can write that these are the oxidation states what we have. And in case of polonium, it is that is +2 and +4, since it is a metal. And that explains that we have written that why it has a metallic character. So this is why it is a metal, because it doesn't show the minus oxidation states. It only shows that +2 and +4. So you can write that like this. Doesn't show this, but it shows +2, it shows +4, it doesn't show +6. It is metallic in nature. So these are the oxidation states. What we can write is, now we can write that these are the oxidation states. We know that. Now we can discuss other properties like that is, we can say that atomic radii. So atomic radii or and ionic radii, I can say that. So atomic radii and ionic radii, I also write that is, the ionic radii will be in form of, that is element -2 I'm talking about. So if we talk about that atomic radii or ionic radii, it increases from top to bottom. So that is atomic radii, ionic radii, that is increases from top to bottom. So we'll say that that will increases from top to bottom in a group. Increases from top to bottom in a group. Top to bottom in the group. In a group we used to say that. So it increases from top to bottom in the group is. So we'll say that it is like this. That is a general order, we can say that follows like that. Melting point and boiling point, we used to say that melting point and boiling point also generally it is generally we used to say that because it is having the non-metal and the metalloids. So we'll say that generally it is we'll say that increases from top to bottom in a group, because the metallic character increases from top to bottom. Non-metals have lower boiling point and melting points. So it increases from top to bottom in a group. Increases from top to bottom in the group. So melting point and boiling point increases from top to bottom in a group. That is how we can write like this. The melting point and the boiling point are, because we won't have to write any such variation is there in like that, because the inert clear effect is more dominating in case up to bismuth, we used to say that. So because polonium is radioactive, so we are not going to discuss the properties of polonium, most of the properties of polonium in this case, as bismuth is, but it is less radioactive as compared to the polonium is. So we used to write that that is the radius what we have written that, and the radius what we are writing is the atomic radii, that is consider that Atomic radii on the basis of covalent character. We have written that this is a covalent radii. Atomic radii, that is a covalent radii. So atomic radii or a covalent radii, I am going to write that. So this is a covalent radii or the atomic radii is. So that is how we are able to write that. Melting point and the boiling points are. If we talk about that electron gain enthalpy, then we'll say that the electron gain enthalpy will be like this. So we'll write that electron affinity. So if I write that electron affinity, it is like this. Electron affinity, it is like this. That is, or we can write that delta electron gain enthalpy. It will be better to write the electron gain enthalpy of that is delta H of the reaction. So I'll write like this. Sulfur has more than selenium, more than that is tellurium, and we'll write that Pe, then it is Po, then it is oxygen. Oxygen has the least electron gain enthalpy. So that is how we can write that the electron gain enthalpy is. So it is like that. And the electron gain enthalpy, if I write the values, we'll write that it is minus 200, it is minus 191, it is minus, that is 194, minus 190, that is minus 174, and this is minus 144 it is. So it is like that. 144 or 145 it is like that. So you can write that it is, that is how we are able to write that the electron gain enthalpy is. So we will say that the oxygen have the least electron gain enthalpy in all these elements. It is because of the electron density which is present on the oxygen atom. So the repulsion of that electron is more as compared to the attraction is. So in all the cases that is exothermic, and electron gain enthalpy means we are talking about that the first electron addition, because electron affinity means the first electron addition. So that is how we can write that electron affinity, the ionization energy, the electronegativity, will say that ionization energy, we used to write that the electronegativity, that all decreases down the group because non-metal to metallic character is increasing. Electronegativity decreases down the group, we used to say that. So it all decreases down the group. We know that ionization energy decreases because due to the increase in the metallic character, we can say that, due to increase in metallic character. So due to increase in metallic character, we can say that, in metallic character, we can say that. So that is how we are able to write that. It is, that is the ionization energy and the electron affinity, and as well as the electronegativity is. So that is how we can write that. So that is about what we can write that the polonium is radioactive. We know that already, and the large difference in the boiling point and melting point of sulfur and oxygen is because of their structure, that is their elemental existence. So the large difference in the boiling point and melting points of oxygen and sulfur, that is acid, is due to their molecular existence. They will have more wonderful forces between because it is existing as an acid, so it will be more wonderful attraction between the molecules of sulfur acid. Molecular structure, it is due to their molecular structure, what we used to say that. So this is their we used to say that the properties, you can say that the properties of element in the periodic table is. So these are the properties of element in the periodic table. We know that oxygen exists as +1 and +2 in the oxyfluorides. We already know that oxygen exists as +1 in O2F2. It is unstable, we know that. And this is OF2 that is existing. That is, in that case, we get that the plus oxidation state of that is oxygen. So that is what we have written here. That is the oxidation state of oxygen is +1 and +2. These are the properties what we required for discussion in that is the oxygen family. So these are properties of oxygen family is. So that is the elemental properties what we have written is. Now we can discuss about their chemical properties. Obviously, if we check out that their reactivity, we'll say that the reactivity of these will decrease, that will increases down the group because of that metallic character increases. So we used to say that, let us check that, how we can write that, the chemical properties. So we can write that the chemical properties of these elements. Let us discuss those chemical properties of these elements. So if we discuss about the chemical properties of these elements, we can discuss like this, that is, you can say that the chemical properties of these elements. So if we discuss about the chemical properties of these elements, we can discuss like this, that is the chemical properties. We can write that. First we can write is, in the chemical properties, that is the oxidation state trend in chemical reactivity, that is we can say that the oxidation state trend. So if we say that the oxidation state trend of that is stability. So trend, that is the +6 oxidation state, the stability of the +6 oxidation state decreases down the group, except oxygen we are talking about, except oxygen, the +6 oxidation state, stability of +6 oxidation state decreases down the group because of it, the inert pair effect. So we used to say that except oxygen, right? Except oxygen, the stability of +6 oxidation state decreases down the group. Oxidation state decreases down the group due to the inert pair effect. Decreases down the group due to inert pair effect. Right? We used to write like this. So it is due to the inert pair effect, the stability of +6 oxidation state decreases down the group in that right now. So we have written that the oxidation states here also, that is these exist in +6 oxidation state, but this does not exist in +6 oxidation state because of the inert pair effect. So there will be some inert pair effect in that case also. It is not that there is no inert pair effect in polonium, but polonium is radioactive. So as I have told you that it is radioactive, so we are not going to discuss most of its chemical properties. Now we can write that is the oxidation state trend. We can write that anomalous behavior of. So it is anomalous behavior of that is anomalous behavior of oxygen. So anomalous behavior of oxygen, we know that we already discussed so many times that why the first element of each group has the anomalous behavior. It is because of the its small size, high electronegativity, then its absence of d orbital, we say that, and its high ionization energy. So it is due to, we used to write that, we can just say this, it is due to its small size. We used to say that small size, high electron affinity and ionization energy. We used to say that electron affinity, ionization energy, and absence of d orbitals, and the absence of d orbital. Absence of d orbitals in this. So due to that absence of d orbitals, we know that it will show the maximum covalency it can show is 4, but mostly it shows 2 covalency. So due to that small size and high electronegativity, due to small size and high electronegativity, it shows small size, that is due to its small size and high electronegativity. I'll write that electronegativity as NEN, that is electronegativity. It shows hydrogen bonding. The oxygen has the ability to show hydrogen bonding. It shows hydrogen bonding. So that was the reason we said that if it shows hydrogen bonding, the H2O is a liquid due to hydrogen bonding, and H2S is a gas because H2S cannot show hydrogen bonding, just the particle remains apart from each other. So there is one of the anomalous behavior of oxygen. It can show the hydrogen bonding when bonded with hydrogen. Obviously, it should be bonded with hydrogen, then only it can show the hydrogen bonding. Otherwise, no. That's why we are calling it as a hydrogen bonding. Due to absence of d orbital, its covalency is maximum covalency can be 4. due to absence of d orbitals. We used to say that d orbitals, its maximum covalency, we can say that maximum covalency will be up to 4. Will be up to 4. But mainly it is, mainly it shows, we say that mainly it shows 2. It shows that is 2. So mainly in most of the compound you will see that oxygen forms only 2 bonds. It doesn't form 3 bonds. If it forms a 3 bonds, then we know that there will be a positive charge in the oxygen atom. So like that, we used to say that it mainly shows its oxidation state, that is its covalency is equal to 2, mainly in the compounds. So we can write like this. Now we can write that the reactivity with the hydrogen. So we write that the reactivity with the hydrogen. So if we talk about the reactivity with the hydrogen, all form hydrides with the hydrogen, we can say that all form hydrides when reacts with hydrogen. So we'll write that all forms that is hydrides, all forms EH2, that is hydrides, when reacts with hydrogen, when reacts with reacts as we'll say that that is element when treated with H2 forms that EH2. So it forms like this. So you can write that they form hydrides. Now we can say that in hydrides the tendency to form hydride is, we used to write the tendency to form hydride, the tendency to form hydrides, we used to write that. So I'm going to write that the tendency to form hydride is that is H2 oxygen has more, then H2S, then it is H2SE, then it is H2TE, then it is H2, that is PO. We used to write like this. The tendency to form hydride is like this. Next we can write is the melting point and the boiling point of hydride is like that. So we write that the boiling point of hydride. So I'll write that. So the boiling point of hydride is the boiling point of hydrides. We'll write that the boiling point of these hydride, water will have maximum hydrogen boiling point because of hydrogen bonding. So I'll write that H2O, it is maximum because of the hydrogen bonding. Then it is H2TE, H2SE, then it is H2S. H2S is already a gas. So its boiling point is, it is a gas at room temperature. So the boiling point is, because this is maximum because of the hydrogen bonding. Water has H2O, has highest boiling point due to H bonding. So it is because of the H bonding, it is the highest boiling point, we used to say that. Right? Next we can write that is the acidic strength. If I talk about the acidic strength, then I'll write that the acidic strength is, we used to say that the acidic strength of H2O is less than H2, that is S, is less than H2SE, then we'll write that H2SE, and I'll write that it is H2TE. So we can write like this. I can write that the reducing character. The reducing character, we'll write that it is reducing character H2O, that is less than H2S, is less than H2SE, is less than H2TE. That is the reducing character. Then I write that thermal stability of hydrides. The thermal stability of hydride is, so the thermal stability depends on the bond energy. So I'll write that that is H2O will be more stable than H2S, will be more than H2SE, will be more than H2TE. These are the order for thermal stability. So it depends on bond strength. Depends on bond strength. We used to say that. Thermal stability means we are talking about the bond energy. We say that. So that's why the reducing character, we say that, and the acidic strength. The thermal stability will be opposite to that of acidic strength because acidic strength is tendency to give the hydrogen. So like that you are able to tell that the reactivity with the hydrogen is and the properties of the hydrogen is. So except water all shows reducing properties such which increases down the road. So water does not show reducing properties. So water does not show reducing property. We'll say that H2O do not show a reducing property. Reducing property, we say that. right? So except that all will show the reducing property. And then we can write that the bond energy, we know that the bond angle is known to us, that is bond angle will obviously also that it will decreases down the group. The bond angle always decreases down the groups. So the bond angle and bond strength decreases down the group. So the bond angle and the bond strength both decreases down the group. That is, we already know that decreases down the group. Down the group, we know that it is like this. That is, H2O will have more bond angle than H2S, will have more bond angle than H2SE, H2PE, like that we can write that. The bond angle of this is 104.5. And this is, that is, we know that it is 92, this is 91, that is also around 91 point, that is 3, and this is 91, we used to say that. That is how we used to write that the bond angles are. So that is how we can write that. The bond angles of these are acidic character is known to us, as I have told you that how the acidic character is. The pK, we can write the Ka values. The Ka values of this is in 10 to the power of minus 3. This is in 10 to the power of minus 4, whereas H2S is 10 to the power of minus 7. And water is 10 to the power of minus 16. We know that. We already discussed that part in, that is ionic equilibrium. This is 10 to, in the power, that is in the order of 10 to the power of minus 3. The Ka values. This is 10 to the power of minus 4. This is 10 to the power of minus 7. And this is 10 to the power of minus 16. So that is how we check the acidic strength of these elements. Now, if I talk about the reactivity with the oxygen, so I'll write that the reactivity with the oxygen, I'll write that. So, with oxygen, all will form oxides, no doubt. We'll say that reactivity with oxygen towards oxygen, all forms two type of oxides. So, all forms two type of oxides. Types of oxides, that is EO2 and EO3. These are the two types of oxides all the elements will form, except it is oxygen, because oxygen is already in a, right now, O2. So we used to say that it all will form two type of oxide, that is EO2 and this. O3 and SO2 are gases, we used to say that. So we write that where O2 and SO2 are gases, whereas and ACO2 is a solid. We used to say that. So this is a solid. ACO2 reducing character. If we check the reducing character of these, because all are oxides, so reducing character, I'll say that that is the character. We used to say that because all will be having, this is AC plus 4. This is also plus 4. So they will have a reducing as well as oxidizing property. So the reducing character between these is SO2 is more reducing than SCO2 is more reducing than TiO2. TiO2 is an oxidizing agent. Actually, TiO2 is an oxidizing agent. It doesn't show the reducing properties. Oxidizing agent, we used to say that. So the TiO2 is an oxidizing agent. We can write like that. So that is about that reducing property is. But we say that they also form that. They also forms that is they also forms the trioxides. Forms trioxides. We say that the trioxides like that is the SO3, that is SO3, ACO3, TiO3. All both the dioxide and the trioxides are acidic in nature. Both EO3, EO2 and EO3 are acidic in nature. We can write that acidic in nature, and EO3 is more acidic than EO2. Acidic in nature, we used to say that, and the EO3 is more acidic than we can write that EO2. So that is how we can write that it is. So that is about the reaction with oxygen is. Next we can write is the next point. We can write the reaction with that is reaction towards halogens. So reactivity towards halogens. So if we talk about that reaction towards halogen, that is halogens, all will react with halogens to form the halides. So forms a large number of halides actually. So all reacts with halogens. with halogens to form, that is halogens X2 to form large number of halides. Large number of halides, and the halides are like this, that is EX6, EX4 and EX, we can write that 2. So they form that large number of halides are formed by this. So these are the halides which can be formed, where X will be, we can say that, where X is fluorine, chlorine, bromine, iodine. So we can write that where X is fluorine, chlorine, bromine or iodine, we can write like this. So we can write that where X is this. And we saw that stability of halide is, we used to say that the stability of halides is like this, the stability of halides. Obviously, if nothing is mentioned, the stability means we are talking about thermal stability. So the stability of halide is, we used to say that the fluorides are more stable than, we used to say that chlorides are more stable than bromides, are more stable than iodides. So that will be the stability order for the iodides. And in hexalides, it is only fluoride which exists. And for hexalides, we used to say that hexalides only fluoride exists as the sulfur hexalides. For hexalides, we used to say that only, that is, we are talking about the hexalide means we are talking about like this, EX6. That is only SF6 is stable and exist. So is stable and can exist. That can exist as a free molecule. The SF6 can exist as a free molecule, we can say that. So is stable and it can exist. All other EX, that is all EX6 is gaseous and have octahedral structure. So that is, we can say that all can be formed but they are unstable, we used to say that. ACF6, they will be unstable because of steric reason. So is stable and can exist for the, due to that steric reasons. So exist. Others, hexalides are unstable because of the steric reasons, we can say that. Others, EX6 are unstable due to steric reasons, we used to say that. Steric reasons. And the HCF6, they are can exist with octahedral shape. Here it exists with the hybridization of sp3d2. If the hybridization is sp3d2, we know that what will be the structure of that SF6 is. It is octahedral structure. So all others are unstable because of the steric reasons. We used to say that because the steric effects, they are not going to exist like that. So that is how we are able to write that. Due to the steric reason, they are unstable. Now we can talk about that among tetrahalides. So among tetrahalides, we can say that. So we can write that among tetrahalides, we are going to write that XCF, that is EX4. So we are going to write that among tetrahalides. So we can write that among tetrahalides, that is like this. The tetrahalides are tetrahalides, that is EX4. Right? So among tetrahalides, we used to write that, that is, we used to say that SF4, that is a gas, ACXF4, that is a liquid, whereas we used to say that the TF4, that is a solid. So these all exist, but they have the seesaw shape. The hybridization is sp3d and having the seesaw shape. All exist with the seesaw shape and sp3 dehybridization. So sp3d hybridization. You know that what is seesaw shape is and sp3 hybridization is. So we can write that they all exist, they are stable. And these all will have seesaw shapes. All elements except, we used to say that all elements except, right? All elements except, we used to write that selenium. They forms, that is all elements that is forms dichloride and dibromides. Forms all elements except this forms the dichlorides and dibromides. Dichlorides and dibromides with sp3 hybridization. So the tetrahedral shape with sp3 hybridization and tetrahedral shape. So they will have a tetrahedral shape. So that is how we can say that their properties is they will be having a tetrahedral shape, and we'll write their structure, how the structure is. So for example, we can write that the well-known monohalides are dimeric in nature. So the monohalides are dimeric in nature. The well-known monohalides are dimeric in nature. So monohalides are dimeric in nature. Dimeric in nature, we used to say that. So they exist as a dibromide and dichloride, that is OCl2, OS, that is SCl2, like that, they are dichlorides. Dibromide SBr2, they are dibromides, like that. They will have the structure of sp3 and this. And even there is a monohalides which dimerize to get the structure like this. That is, we used to write that. For example, we can write that the monohalides, for example, of monohalides, we used to write that. For example, the monohalides, we used to write that. You can write here. So the monohalides, I'm going to write it is like this. The monohalides. Monohalides, the example of these monohalides is that is S2F2. You can write that S2Cl2. You can write that S2Br2, like that Br2. You can write that. Then you can write the AcCl2, that is Ac2F2, Ac2F, that is Cl2, Ac2Br2, like that we can write that. But these are unstable. We have written that it is unstable, and since they are unstable, because that's why we have written that. Except that, since they are unstable, so they get converted into, they will get disproportionate. So they undergoes disproportionation. Unstable, so undergoes disproportionation. So they undergo disproportionation as disproportionation. We can write like this, that is, you can write one of the example for the disproportionation. AC will write that is disproportionation. Ac2Cl2 will disproportionate to give you that AcCl4 plus Se. So you can write that the disproportionation reaction is like this. So that is how it converts into, that is AcCl4, and it will form, that is AcCl4 plus Ac. So Ac2Cl2 will disproportionate like that. So the monohalides, the dihalides, they get disproportionate like this. Even that is, this is monohalides, and the dihalide is like this, AcCl2, that also get converted into, that is AcCl4 plus, we'll get that it is Ac. So this is dihalides. So it's dihalide as well as the monohalide, they both are unstable. So that is how we can write that. This is dihalides. Here we can write the dihalides also, example for dihalides. So they exist in dihalide as well as monohalide shape, like that. So we can write there halides part, that is like that. Next we can write that is that is the disproportionation part. So this is about the halides of these elements, and that is about their chemical properties. Now we can discuss that how we can prepare the pure oxygen as well as pure sulfur. The elements are formed, and we can say that what are the compound of oxygen and sulfur is. So these are the properties of these elements which are present in this group. So that's all in this class. In the next class we'll discuss about the preparation of the compounds of the elements and the element is. So how we are going to write that, we'll discuss that in the next class. So that's all in this class about the oxygen. That is, in the next class we'll discuss about the oxygen. So in this class we have discussed the properties of this element, the physical properties and the elemental properties. That's all in this class.